Okay, we have just a couple more slides on the gas to officially wrap it up, and then we're going to go off to the next chapter, which will be 15. I think we're going to go next. So obviously we talked about a lot of gas laws last time, and we talked about partial pressures and several different types of partial pressure type problems involving where you can use the ideal gas law basically to solve for the pressures of each gas separately. And again, part of that idea is the idea of the ideal gas, where even though there's multiple gases in the same container, it's basically assumed there's really no interaction between the different gases, so that you can kind of assume that they are in there by themselves. So you can do a individual sort of ideal gas law for each of the gases there. That will get you your partial pressures. And again, your total pressure there is going to be adding them together. We also saw a formula where if you maybe don't have enough information to go into the ideal gas law, but you have enough information to get the moles of the gases. Also, if you have just one piece of pressure sort of information, you can use the partial pressures equal to that mole fraction, where we have partial pressures equal to the mole fraction times the total pressure. Call that A. And again, the mole fraction is really just a kind of like a percentage without multiplying by 100. So you take the moles of the gas you're interested in, you divide by the total moles, and then you times it by the total pressure if you have that number, and that'll give you their partial pressures. We lastly saw a situation where very commonly in lab, like we did in those couple of experiments where we collect the gas with water involved, usually will give you a mixture of water vapor and the gas that you're interested in. And that is really a kind of a subtraction sort of problem that happens where the pressure of the gas plus the vapor pressure of water, which you can look up in a table. So oftentimes you're just involving basically just subtracting at that point the total pressure minus the vapor pressure of water that you get from the table. Any question on any of that partial pressure stuff we talked about last time? All right, so just kind of finish up here with these couple of slides. The kinetic molecular theory of gases talks a lot about some of the stuff that we covered through the different gas laws. It says gases consist of tiny particles like atoms or molecules. Number two is that the particles are small compared to the distance between them, and the volume of the individual gas molecules are assumed to be negligible. As we've been talking about, that is pretty much one of the things that makes something an ideal gas, is this idea that when we think about sort of the gas molecules themselves, it's more important sort of the volume of the container they're flying in versus the actual volume of the gas individual volumes. And that's why in a lot of problems, what they'll talk about is the volume of the container the gas is in rather than the specific volume there of the gas itself. Excuse me. The particles are in constant motion, and again, it's those collisions that's going to cause the pressure that we assert with gases. Number four is really the sort of other thing that makes something an ideal gas and what sort of considered an ideal gas. And that's what we were just talking about with our partial pressure situation. Again, it's assumed that although we may have multiple gas molecules in the same container, there's really no attractive force or repulsion type forces under sort of normal pressures and temperatures. And that's sort of an ideal situation. And that's what really allows us, as we were talking about here, to do that calculation with the ideal gas law sort of individually for each gas in a mixture of gases in the same container. The reason that's important is if there was some type of interaction that would happen between the gas molecules, that would affect the pressure that would happen. So, for example, if we had some type of interaction, say, and this is like the wall of the container there, we have this gas molecule and this gas molecule. With no interaction, pretty much this gas molecule is just going to go and slam into the wall of the container there and cause some pressure. But let's just say, for example, there was some attractive force between the different gas molecules. What would now happen is that guy would actually be a little bit attracted to the gas molecule behind it, and that would probably slow it down there and cause maybe less collisions occurring and may have an effect on the pressure. Vice versa as well, if they were sort of repelled by the other gas molecules, they may want to get away from those other gas molecules, and that would also have an effect maybe on the collisions and also on the pressures that would occur. So in ideal situation, pretty much everything we do in here, And in most cases, we don't have to take that into account, and that's sort of what makes something an ideal gas. A real gas or a non-ideal gas, which you'll learn about more in 1A, you do have to take those things into account, and that happens at really, really large pressures and low temperatures because if you remember sort of our high pressure, small volume relationship of Boyle's law. So if you have really, really high pressure, you're going to have a very small volume. And that means all those gas molecules are going to be near each other for a much longer period of time. They're going to have to interact with one another. And if you have a really small volume, the size of the gas molecule itself is going to come into play as well. So under real conditions or non-ideal conditions, which happens at really large, super large pressures and low temperatures, you do have to take those things into account. As you'll see in 1A, if you take it, turns the ideal gas law into what's known as the van der Waals equation, and it's kind of a scarier looking of the ideal gas law. There's a lot of constants you have to put in there specifically for each gas to sort of do the calculation. So the reason we use the ideal gas law in most situations is under normal pressures and temperatures, even if you get a little bit higher than normal sort of pressures and temperatures, the deviation from sort of ideal situation and non-ideal situation is really, really small. So the ideal gas law, the way it is, the PV equals nRT, is more of a universal sort of gas law that allows it to be used in lots of situations. It's only when you get those really large pressures and small temperatures that you have to take the others into account. The fifth thing that you need to know is, again, that the kinetic energy of gas molecules is related to temperature. So as we've been talking about, obviously, in this chapter, the higher the temperature, we would expect those gas molecules to be flying around faster. And sort of the lower temperature, it would be flying around slower. And obviously, that will have a direct effect on the pressure, especially if we are in a rigid sort of container where the volume will not move or adjust for the increase or decrease in temperature. So remember, as we talked about, sort of in a constant volume, which is Guy-Lussac's law, as we increase those temperatures, we would expect an increase in the pressure as we would have more collisions. As we decrease the temperature, we expect less collisions and the pressure to come down. That is sort of fixed in a constant pressure situation, like we talked about with Charles' law. And again, it's that volume aspect of it that's able to adjust as the temperature adjusts to allow the pressure to remain constant. So in that Charles' law situation, as we saw, as the temperature increases, the volume will also increase. And again, that's going to allow more room for everybody to fly around. Even though they may be flying around faster, it's going to keep really the rate of collisions constant. And that's really how it's able to keep that pressure constant. And again, we just don't get that when we have a fixed volume for the gas, because the volume of the container really cannot adjust to keep up with the temperature, either up or down. Any questions on any of that stuff there? I think those are the last couple of slides. All right, so that should wrap up chapter 13. Like I said, we're going to actually go to 15 next, and then we'll come back up here to chapter 15, which is solutions. And like I said, we'll go back to the other ones after this, but I think this will be more relatable to what we're doing this week in lab. So let's talk a little bit about solutions and aqueous, which is a solution. As we probably touched upon, again, aqueous is those guys that get the AQ symbol next to it. And that is a solution. And again, a reminder that a solution is a homogeneous mixture of two or more substances together. So it looks the same throughout. Pretty much all those reagents in the dropper bottles are solutions in the most part. A solution, and again, is made up basically of two things. There is the solute, which is really the smaller part of the solution. And there's the solvent, which is the larger part of the solution. So you need both of those things to have a solution. And I think we've talked about it before, but once again, just a reminder, the difference between, say, something that is a liquid and aqueous. And the difference there is, if something is a liquid, that is a pure liquid, so one substance by itself, like water. But to make a solution, which will get the aqueous symbol, you do need to mix two things together, hence the idea it's a homogeneous mixture. And we need to put, say, something like solid sodium chloride. That will dissolve in water, and that will make a sodium chloride solution that will get the aqueous symbol. So something with aqueous means really there should be those two parts together, kind of something that is dissolved in a solvent, a solute that's dissolved in a solvent. The solute for a solution is always the name of it. So if I have a sodium chloride solution, the solute is sodium chloride. If I have a potassium chloride solution, potassium chloride would be the solute. I would also say, as we'll talk about here, for most parts, water is a very good solvent for a lot of ionic compounds. And a lot of things, water is the solvent. But it's not always the solvent. So it does have to be sort of the right situation for water to be the solvent. There are certain things that water would be a really terrible sort of solvent for, some of which we saw last week when we did that second experiment there with the solutions. And like when you took something like, I think the iodine, and you try to put deionized water and you maybe saw the iodine didn't dissolve. It's not a great thing for non-polar things, but water works really well for ionic things and also things that are polar. And once again, the reason why it works really well for those two things is because water, again, is a polar molecule. And a polar molecule means that, again, it has a separation of charge and it has a negative side, which is the oxygen side of water, and the hydrogen side is more positive, and that's due to the overall unequal sharing of electrons, like when we talked about bonding and polarity and molecular polarity. And that is incredibly important for why certain things are soluble in water and maybe why certain things are not. And really, pretty much all solubility and how things interact with one another. They interact with one another through these intermolecular forces. And these are the forces between two molecules, basically how they interact with one another. And all intermolecular forces, and there's different types. So, for example, water, a lot of times we'll use what's referred to as hydrogen bonding. There's dipole, and there is dispersion forces. So, there's hydrogen bonding, which is a type of intermolecular force. There's dipole. And both of these are for polar molecules. And there's dispersion forces, which is really for nonpolar molecules, is pretty much what they use. But all three of those different types of intermolecular forces, they all use really the same sort of attraction. And it is a very simple attraction of the positive side of one molecule is attracted to the negative side of the other. So electrostatic sort of attraction. And these type of forces can be between molecules that are the same, can be between molecules that are different. So you could be like the force between two water molecules. The force between two water molecules is hydrogen bonding. And when two water molecules come together, the positive side of one is attracted to the negative side of another. And that is what's known as hydrogen bonding right there. And that is the force, again, that holds those two water molecules together. By the way, just so you know, in order to have hydrogen bonding, you need a bond between hydrogen and nitrogen, oxygen, or fluorine. And if you look at the periodic table, nitrogen, oxygen, and fluorine are the most electronegative elements you can have, right? Up and to the right, pretty much on the periodic table. And because of that, what happens when hydrogen is directly bound to one of those elements, it creates a really polar charge. A really polar bond is, I guess, a better way to say that. A really polar bond. So, for example, if you think about the HF bond, when we did bonding, maybe you don't remember or not, but the difference in electronegativity between hydrogen and fluorine was like 1.9, and that's almost close to ionic, right? So that's a very big separation of charge. So you're going to get a pretty good positive side to that bond and a pretty good negative side to that bond. So it does need to have that hydrogen directly bound to one of those elements in order for it to participate in hydrogen bonding. Sometimes people think when they see something, for example, like this, like CH4, like it's got a ton of hydrogen, so it should be able to hydrogen bond. And it cannot hydrogen bond here, and that's because a couple of things. First off, that molecule itself is actually nonpolar, right? Symmetrical geometry, and the individual bond between carbon and hydrogen is considered a nonpolar bond. So this is really a neutral bond here, neutral molecule. So it cannot hydrogen bond, even though it has a ton of hydrogens there. So it's got to be that hydrogen that is directly attached to a nitrogen, oxygen, fluorine for it to be able to do so, because that's going to give it a really good separation. What this guy has to do, this guy is a nonpolar guy, which means he's going to use dispersion forces when he tries to interact with molecules. And dispersion forces are pretty much the weakest of all intermolecular forces. And the way dispersion forces pretty much occur is they need something to happen to give that nonpolar guy an opportunity to separate his charge out. So with nothing happening, all its electrons are going to be nicely equally distributed. There's not going to be a positive side to the molecule. There's not going to be a negative side to the molecule. So there's no way for that molecule to really interact really well. So in order for dispersion forces to sort of happen, what happens is, for example, we have a nonpolar molecule and another nonpolar molecule. And electrons, because they are moving around, can in some cases all decide we're going to vacation, over here on this side of the molecule. And if they all end up on the right-hand side of the molecule, just temporarily kind of all flew over there into that area, that is temporarily going to create a positive and negative charge on this guy that normally did not have one. And the result of that is if he's still next to this nonpolar guy, the electrons in this guy is going to go, I want to go away from you. And it's going to create a temporary separation of charge in this other nonpolar molecule. And now these two guys that started out with basically no charge temporarily creates charges, and now they have a way to interact. The reason why these are very, very temporary is at some point those electrons are going to fly back the other way, and that charge is going to kind of shift again, and that's going to allow those guys to kind of break apart and not really maintain that interaction. It will create new sort of charges, and they'll break apart and come apart. And that's why dispersion forces are really, really weak, because it relies upon something like that happening. It also can temporarily happen if you put a polar molecule next to it or an ionic guy next to it, because those guys have charges or separation of charge, and that can happen. And that's why we see something like, oil and water, for example, or oil and vinegar sort of mix for a bit, and then they sort of separate out. And again, they could temporarily sort of interact with each other, but they have no way to maintain that. And that's very different than what happens with something like water or any type of polar molecule. A polar molecule, no matter what happens, will always have a dipole moment, and it always has this separation of charge, which means it's good to go. It doesn't have to wait for anything to happen. It's got a positive side, it's got a negative side, so it's able to interact right off the gate there, and nothing's going to change. The water will never switch out and not have a positive side or negative side, so it always has that fixed sort of positive side and negative side, which allows it to interact really well. And they're always ready to interact either through hydrogen bonding or dipole-dipole. So what is the difference between hydrogen bonding and dipole-dipole? Dipole-dipole is how polar molecules interact with each other, and those are polar molecules that do not have the ability to hydrogen bond. So these are just polar molecules with no ability to hydrogen bond. So polar, no ability to hydrogen bond. So out of all these three types of forces, the hydrogen bonding is the strongest intermolecular force. Dipole-dipole is the next. And the weakest out of all of them are dispersion forces, which are, again, these more really temporary guys. So a lot of organic compounds use dispersion forces like methane. And if you think about a lot of the organic molecules, especially the first several, they're all pretty much gases. Methane, propane, butane, all those guys, they're pretty much gases because they're held together by these really weak intermolecular forces, which means you just look at them and they can go into the gas phase really easily. Even things that are organic, for example, which are carbons and hydrogens mainly, organic that are liquids and stuff like that, they're oftentimes very volatile, which means they can jump into the gas phase really, really easily. So you could have a liquid, and then because they're held together by a very weak force, they could jump into the gas phase really easily. That's why when you work in organic chemistry, they usually throw you in a fume hood, because a lot of those chemicals can go into the gas phase really, really quickly, and flammable, by the way. So they don't want those fumes and vapors sort of going down the bench, and maybe something A, knocks you out, or B, catches on fire because it's flammable as well. So a lot of times if you go to organic, you'll be in a fume hood, because even if you are using something that is a liquid, it can go into the vapor phase really easily, like those maybe hexane and heptane stuff that we used the other day. You could probably smell them pretty good when you opened it up, right? And that's the reason you can smell it, is you can jump into the vapor phase really, really easily, right? So that's why a lot of those things happen. Any questions on intermolecular forces there? Sort of a preview-ish relation here. So these type of intermolecular forces, as we were talking about here, are really important for how things interact and why things are soluble in each other. So for example, water here, which is polar, is soluble. Our ions are soluble, or ionic compounds are soluble in it, because essentially what will happen is those ions will be picked off by the water molecules. And the negative side of water, which in this case is the oxygen, the negative side pretty much, will be attracted to the positive ion, like the cation. The positive side of water, which is the hydrogen, will be attracted to the anion. And that is, again, how something dissolves. And this is also why, again, it is a physical change when we dissolve something. That is because the ions are still there. We just can't see them, because there is a ton of water molecules. And there's so much water molecules, they're actually able to pull off the ions from each other. And that's a pretty good feat, because the ionic compound in a solid phase is held together by very, very strong electrostatic attraction, positive, negative attraction between the ions. And the only way to really pull them off is you need a lot of water molecules in there to kind of squeeze each of the ions off. And as they do, they keep these ions separated from each other. So these ions are, again, separated from each other in a solution. This is essentially why we write aqueous, because they are surrounded by water molecules. And those water molecules keep them separated, and also allows us to not visually see it anymore as it has dissolved. And that is what keeps those guys apart. We know, again, that if we get rid of the water, like we've done in a couple of experiments where you evaporate off the water, you pretty much get rid of all these interactions here. And now there's really nothing stopping those two ions from coming back together. And that's why you will see the solid appear after you evaporate off the water, like in some of those earlier on experiments where we had like the evaporating dish on the beaker of water and we kind of evaporated everything off. The solid comes back. Again, why is a physical change? Because technically everything is still there in their original form. So this is the process. As you can see, water molecules come in. This is what an ionic solid looks like in a solid form. It is an arrangement, a pretty ordered arrangement of the ions, where they maximize the positive and negative attraction in the solid state. But these water molecules come in basically and start grabbing up all of the ions there. You help it by doing all three of those things, or some of those things that were on the post-lab question, right? You stir it, right? Helps it dissolve because you throw more water molecules all over those ionic solids. You could also heat it up, which provides more energy, right? And things moving faster, so it's going to allow it to dissolve. And the grinding part, which you probably don't do in a lot of cases, but maybe if you grind it up, you create more surface area, right, for water molecules to get to help increase the dissolving process. Maybe. And that this is, again, the process of taking an ionic solid and dissolving. Those are water molecules, the red and white guys floating around. Again, they're going to come in basically and grab off an ion and surround it. And again, that is the process of it dissolving there as it goes through. Again, by stirring and doing those things, providing more energy, providing more water molecules all over the whole thing, it's sort of relaxing watching the molecules float by. So let's talk a little bit about solubility and the types of bonds that we've talked about before. Ionic, obviously, as we've talked about many places, is between a metal and a non-metal, and we get that from a transfer of electron. And what's holding that together is electrostatic attraction, opposites attract. Covalent bond between two nonmetals. That's where we have sharing of electrons. And that's going to result in either a polar covalent bond where we do have that separation of charge, or we're going to have a nonpolar bond, which again will be equal sharing of electrons and really more of a neutral guy. So, how do we know the difference? As we talked about, just a reminder, we do look at the difference in electronegativity between the two atoms within the bond, and that can result in either a polar or nonpolar bond. Why is this important? There are a lot of molecules, for example, that are mainly nonpolar in the sense of the bonds that are present, but there is polar. So there's a lot of organic compounds, for example, where you take something like methanol here, which if you think about it sort of realistically, when we look at something like methanol, this part of the molecule here is pretty much nonpolar. It's got all the carbons and hydrogens happening, but it does contain this little part right here, which is the OH group. And that actually is a polar bond, as we know from difference in electronegativity, oxygen being more negative, hydrogen being more positive. So we also have in that case a hydrogen that's directly bound to an oxygen, which means it can participate in hydrogen bonding. And that's why something like methanol, which is an organic molecule, a small little guy that has a nonpolar part, also has a polar part. And that's why methanol, which I think is also what we used the other week there in that experiment, was soluble in water because it can now have a way to interact with water the same way that water interacts with other water molecules. And they're able to hydrogen bond between each other. So the oxygen, for example, of water attracted to the hydrogen there in methanol. And that's going to allow it to work, even though it has sort of a nonpolar part to the molecule. But because it has this little polar part, it allows it to interact. So the polarity of bonds that you see within molecules are really important for whether or not they will be soluble or insoluble, be able to sort of mix together. And as we see here, and as we talked about a little bit last time, the more ways that one molecule can interact with another, if they can interact the same way that they interact with themselves, is going to make it really, really soluble, and they're going to really be able to mix really well because they're essentially using the same type of interaction they use with themselves. It's really only when we get sort of differences in that, where we get things trying to use very different ways of interacting with other molecules, very different than how they interact with themselves, that we get things that really don't mix together. So the polarity of bonds that we see in molecules are really important for that. So things that are soluble in water, again, ionic guys are definitely going to be soluble in water, like the video we just saw, their animation and what we've been talking about, because water basically can still do that positive negative attraction. It will be able to surround the positive ions and negative ions. The beauty of water is it has a positive and negative side, which allows it to work with both ions in an ionic compound, the positive guy and negative side, to just kind of switch around the water part that's interacting. Uh, we also see in non-ionic things like sugar and ethanol that they're able to interact well with water. I drew methanol a second ago. Ethanol looks like this, which also is very similar looking. So that's ethanol. And once again, if we kind of break this molecule up, it sort of has a non-polar side. But once again, it has this polar OH group, which is again exactly what we see in water. And that is why something like ethanol is also going to be soluble in water, because it is able to do that interaction, little hydrogen bonding happening. So things that have parts that can interact, and it can, you see in these two examples, can just be a very small part of it that's able to interact with water, will typically be soluble in water. Now, the solubility of something, say like methanol or ethanol and organic molecules, for example, as you increase the number of carbons. So, for example, if I had something like this. Clearly, we got a much different thing in a sense. We have this nonpolar part, which in comparison to our others is much, much bigger. And this does create a problem in terms of solubility because it's too big. And what happens is that nonpolar side versus the really small polar side, the nonpolar side gets in the way. Sometimes referred to as steric hindrance. It's just in the way of the water molecules being efficiently able to get in there. And it, frankly, it's just too large of a molecule to be really soluble in water. So when you hit about, I would say like 4 or 5 carbons with an OH group on it, which are alcohols in organic chemistry, solubility starts to really drop to almost nothing. As you get to 6 or more carbons, pretty much is not going to be soluble. And it's because the nonpolar side of that molecule now is just too big. So you can kind of think about it like this. In order for something to be soluble in water, it needs to be small enough to interact well with water, because essentially what it's replacing is, before water dissolves or you dissolve anything in water, there's a bunch of water molecules bounded together, which means you need to get rid of some water molecules to allow something to come in to be dissolving in it and be soluble in it. And these things get really, really large, just doesn't fit very well. I sort of equate it to, like, you know, you could get like a car, normal car or normal truck, maybe a car-ish, into a garage, right? But you try to put a semi truck into a garage, you get some of it in there, but it's not going to fit very well, right? And it's going to hang out. It's kind of the same idea. It's just, although it may work a little bit, it's just not going to work very efficiently at all, because just the overall size of that molecule is just too big to interact with the really small water molecules and stuff like that. So there is a limit to solubility, even with things that have these little bonds that can interact. The larger the molecule gets, the solubility typically also starts to decrease. In addition, the more OH groups that you put on there, for example, the greater the solubility is. So if you have something that has a bunch of OH groups, it will increase the solubility of that particular compound, because everywhere there's an OH group, it gives water an with it. So here's our methanol. Again, hydrogen bonding here, our bond between hydrogen and oxygen happening here. It is essentially just the opposite charge that's happening here between the positive hydrogen, negative oxygen. That's going to make that really strong attractive force. Here's our ethanol again, and how it's interacting once again through hydrogen bonding between these guys. So what about oil and water? Do they mix? They do not, because oil is essentially long chains. I won't draw it, kind of like I just drew on the other page without the OH at the end. Just really long chains of carbons and hydrogens. And as we talked about, the carbon-carbon bond's nonpolar, carbon-hydrogen bond's nonpolar. So what you end up with is this really long chain of carbons just going one way and another, nonpolar, no way to interact really well with water. And as we maybe know, oil is insoluble in water, and what typically happens is they end up floating, like the oil ends up floating on top of the water, like you've had an oil spill. And that is because, although they can maybe interact for a very short period of time, over the long period of time, there's just no way for them to maintain that. And that is because water is using hydrogen bonding, oil is trying to use dispersion forces. So you have a very big difference in the forces that they're using here. Water using our hydrogen bonding, and oil using dispersion forces. And if you remember, this is the strongest. That's pretty much the weakest. And they have no way to maintain that interaction, because oil will constantly kind of break apart, come back together, break apart. It has no way to maintain that. Water is fixed with the positive, negative side. It's good to go. But they're using very different types of intermolecular forces. And that's pretty much, again, what nonpolar molecules will use, which is that dispersion forces. So because of that, as we talked about last time during that lab, and also here today, we'll hear it a lot, the idea of like dissolves like. So things that use similar intermolecular forces will be soluble in each other, and things that do not will be insoluble. As we did the list, I think on the board the other day, once again, soluble things, pretty much your ionic and polar, because they're able to do like we saw with the ions in the water. Polar things and polar things will be able to be soluble in each other, and even non-polar things and non-polar things will be soluble in each other. So that's sometimes missed by people because they're like non-polar, they think insoluble. But if you take something that's non-polar and put it with something else that's non-polar, like I think we also did hexane and heptane the other day, right? So those are two non-polar guys. They will mix because they're both using the same type of intermolecular force. They're both using dispersion forces, which makes them very soluble in one another. Again, it's only when you cross over, pretty much. If you go polar and non-polar, you're going to get some insoluble happening here. And pretty much what's going to happen is one's going to probably try to use hydrogen bonding or dipole-dipole. The other one's going to try to use dispersion forces. Vastly different ways of interacting with one another, and they're not going to mix really well. So that's why water is a really good solvent for a lot of things, besides the fact that it's not toxic for the most part. It works well with ionic things and polar things, which is a pretty big chunk of molecules that you might come across. But water would be a really terrible solvent for something that is non-polar, which you also, again, probably saw, like we talked about there with the iodine and the water, they didn't mix. It's not going to work really well. But when you did the iodine, for example, and the potassium permanganate, turned out nice, pretty purple. And that's because the solid mix, because potassium permanganate is ionic, so it's able to work well with the water. The I2 is non-polar, so it's not going to work really well with the water. They won't be able to interact with one another. Any questions on that there? So here's a couple of pictures. So although we do see here sugar, which is a relatively large molecule, what allows it to be really soluble is it is pretty much littered with OH groups. And everywhere there's an OH group, you're just increasing the solubility. You're also giving water tons of places to interact with it. So as we know, sugar is really soluble, obviously, in water. It will dissolve because of that, even though it's a relatively larger molecule. Here we have pretty much what makes up oil, which is, you can see here, just really a long chain of nothing but carbons and hydrogens together. And that's non-polar and not going to interact well with water, because water's looking the hydrogen bond and this guy's looking to do a dispersion forces, and thus we get our typical separation that will occur over time there with our water and our non-polar guy like our oil. Typically speaking, non-polar guys or organic guys usually end up there on top. Kind of the water layer there ends up on the bottom. If you remember back to when we did that those experiments where we did like the different layers of the halogens, and we looked for different colors in the top layer and the bottom layer. Top layer was always the layer that had like the I2, the Cl2, and the Br2, because those were non-polar. So that was the sort of the top layer, the organic layer. And that's why they were up there, because we put, I think, hexane when we did that experiment, which is non-polar. So that non-polar guy would be attracted to the top layer, and that's why they were always in the top layer in that experiment, because they are soluble in each other. Bottom layer was the water layer, where we had things like sodium chloride that we put in there, right, to see the switch, or sodium bromide, and where the ions ended up was the bottom layer of those test tubes. So that's because of this sort of separation that was occurring. So when we talk about things being soluble in each other, there are a couple of sort of things that we look at. If something is soluble in one another, a solute is soluble in a substance, they will pretty much mix. And we do use soluble and insoluble a lot of times for everything, but a lot of times specifically for solids dissolving in liquids, for example. And if something's insoluble, what would happen is we would expect it not to dissolve. So we would expect a solid to still be there. We also use a couple other words when we did the lab, which sometimes are used for liquids and how they mix. So miscible, right, is when two liquids mix. And miscible is when two liquids do not mix. And if we're dealing with two liquids together, if they do mix and they are miscible or soluble, miscible, whichever way you want to do it, they will look basically like one layer, right? Because everything will interact well with each other. If they're immiscible, you'll see some layering that will happen, which means they're insoluble or immiscible. So sometimes, again, people will use miscible for soluble, immiscible for insoluble when you're kind of talking liquid and a liquid sort of mixing or not mixing. There's usually a limit to the solubility of one substance in another, and solubility, for example, of say like solids and liquids, or how much of a solid you could get to dissolve in water at a particular temperature, is related to the temperature. So typically, if you increase the temperature, you can get a lot more solid to dissolve in a liquid like water. And if you decrease the temperature, you can get less solid to dissolve. That has a lot to do with a couple of things we talked about. Obviously, increasing temperature gets things moving faster, more energy, going to be able to sort of get more of that solid to kind of dissolve. Less temperature or lower temperature, right? Things are going to be moving slower, less energy. So less water molecules going to be able to kind of pluck off those solids as you go through it. Gases are always soluble in each other. Gases are always soluble in each other because gas molecules are constantly flying around, which means they are constantly mixing in the same container. Some liquids are also usually soluble, and those are what we basically just talked about. Polar and polar guys are soluble in each other. Non-polar and non-polar guys will be soluble in each other as well. Any questions on that there? So that idea of like dissolves like, which is really important, and that's just what you want to think about when you're trying to make a prediction of these things. Will they sort of mix together? You know, are you mixing two polar things? Are you mixing two non-polar things? Are you mixing a polar and non-polar things? Are ionic and non ionic and polar versus ionic and non-polar? Will they sort of mix? Um, when we talk about a solute and a solvent, the higher the temperature, the larger solubility of a solid in a liquid, as we just talked about, because of the temperature and energy. At lower temperatures, we have a larger solubility of a gas in a liquid, and that is because if I have a gas in a liquid and it's at a lower temperature, we would expect it to be moving slower, which means it's going to be moving through this liquid part a lot slower, and that means it will stay mixed for a lot longer period of time than if you had a higher temperature. Your gas molecule would have a lot more energy and it would just sort of shoot right out, right? And it will not stay mixed for a very long period of time. In terms of gases, pressure plays a really important role as well. The larger the pressure, the higher the pressure, the larger the solubility of a gas, as well. And that is because, as we talked about, at really large pressures, we are going to have really small volumes, right? Which means our gas molecules are going to be near each other and they're going to be constantly mixing for a lot more period of time. Any questions on that there? So a couple ways that we can describe solutions is saturated solution. And again, a saturated solution is a solution where pretty much you've hit what's sometimes referred to as the saturation point, the point where no more solid will dissolve in a solvent or a liquid at that point. If you try to dissolve more solid at that point or solute, it will not dissolve. It'll pretty much just kind of pile up. So again, if you take some sugar packets and you kind of dump them in like a glass of water, you can probably get the sugar to dissolve pretty well. If you take the Costco size of sugar and dump it into that one glass of water at some point, you could stir all day. That sugar is not going to dissolve, right? Because you do not have enough solvent to get it to all dissolve at that particular temperature. So a saturated solution is pretty much that point where you hit exactly based on that temperature how much of that solute you could get to actually dissolve. Before you get to that point, you have what is referred to as an unsaturated solution, and that's pretty much what it sounds like. You have not hit that point yet. So if you take more solute and try to dissolve it, it will continue to dissolve until you pretty much hit a saturated solution. So continue to dissolve until you hit a saturated solution, and at that point it will not dissolve anymore. So saturated, you pretty much hit the max that you can get there to dissolve at that temperature. Unsaturated, you're not there yet. You can continue to dissolve that solid. Any questions on the difference there between the two? Now, a third type of solution is like what we talked about and saw and did demoed the other day, which is a supersaturated solution. And in a supersaturated solution, you have too much solute dissolved at a temperature. So, as I talked about last time, and how a supersaturated solution is typically made is you make like a pretty saturated solution and you kind of heat it up as you're dissolving the solvent or the solute in it. So as you're heating it, you're dissolving more and more solute, and you're able to do that because you're heating it. So you're increasing the temperature, which means you could get more of that solid at the higher temperature to dissolve. And typically after you do that, you then kind of leave your solution alone. You let it cool back down to sort of whatever room temperature or cooler temperature. And when you do that, you were able to get all this solute to dissolve at this higher temperature, and it's dissolved. It's a solution. And as you cool it back down, the solubility of that solution is actually changing. It's becoming less and less. You should not be able to get that much to dissolve. But it's kind of too late at that point because you already got it dissolved at the higher temperature. So as it drops back down in terms of temperature, you now have a solution, as we saw in that demonstration, that is very unstable because, frankly, you have way too much solid dissolved in it. And at the lower temperature, there should be much, much less solute dissolved. So as we saw, you could add just one small crystal to it, and what will happen is all the solid will go out of solution because it's like, well, that's like way too much at this point for sure at this lower temperature. And it'll go from a solution to a really sort of rock hard sort of solid, as we saw in that flask. Also got really warm when we did it. It's really unstable that sometimes before I drop the crystal in, like I did the other day, just gently putting it down on the bench or just moving it, it's enough to get it to just jump out of solution. It's that unstable. You don't actually sometimes even need to add the crystal to it. So one more time in case you missed it when we did it, that's pretty much the same solution that we had. And again, that's a supersaturated solution, and that is your sodium acetate solid. And again, you can see they're just going to go grab one little super small amount. And now when that hits, it recognizes way too much solid in there. And that's, again, all the solid or solute coming out of the solvent in that case. And as we saw with our flask, look kind of similar. Again, it went from a liquid, basically our solution sort of state, liquid state, to that solid, super slow motion, in case you missed it for the replay there. All right. And as I said, this particular example, really hot, which meant it was exothermic sort of process, right? Making that solid, which makes sense, right? In order to make a solid, things need to get closer together, less energy. That means that energy has to be released, right? And that's why it's more of an exothermic sort of process. You can actually feel the heat because as it comes into a solid, in order to slow down to come into that solid state, you got to release that energy to do so. Otherwise, it would stay in the liquid state because it has more energy, right? So that energy is being given off. All right, other ways we could describe solutions is concentrated and a dilute solution. A concentrated solution is typically a solution that contains a large amount of solute in it. A more dilute solution, which is like we use in lab, a lot of our solutions that we use are more dilute, and that has a relatively small amount of solute. How we go from one to the other is a lot of times we add water or solvent to it, and that makes it more dilute than what you started with. So kind of like you get your drink right before you come to class with your ice and your soda, and you taste it, and it definitely tastes good, right? It tastes like soda. After you go to class, you come back to your car, right? All the ice is melted, right? You still take a drink just to see. Then maybe you regret it afterwards. Who knows? But it doesn't taste as good because all the water from the ice has now diluted down your soda, right? And it's more dilute in that case. But you got nothing else in the car. You got to drink it. Okay. All right. Let's talk then about concentrations and some important concentrations. We're going to talk about some percent concentrations here for solutions. The first one is mass percent, which is sometimes abbreviated percent M/M. And that is the mass of the solute over the mass of the solution times 100%. And it's really important in these type of problems. It's actually the bottom part here, which is the mass of the solution. Remember that the solution is two parts. It is the solute and the solvent. So you want to make sure on the bottom there that you actually get both of those values in your calculation. The reason why it's important is it is very common in these type of processes or problems that they will give you that information separate from each other. So they'll give you the mass of the solute, they'll give you the mass of the solvent, and again, you need to make sure that you add them together. Common mistake, people will just divide by the solvent because they see the larger number, but you do need to make sure you get them together, and it's very commonly given different. So if I had, for example, a 4.25% by mass, say sodium chloride solution, that would mean that I have basically 4.25 grams of sodium chloride in 100 grams of solution. And this is useful as sometimes in problems you may want to use it as a conversion factor. So you can assume 100 grams, for example, and you can use it like a conversion factor like that. You could also flip it around if you needed to use it in dimensional analysis in the back way. Solution would have 4.25 grams of sodium chloride. So sometimes it's easier or to sort of see the units if you kind of do a dimensional analysis, and you might need to kind of turn it into a conversion factor. Again, you could just assume 100 and it would be there. It is mass to mass, which means both units are typically grams over grams. They technically could probably be any mass unit, but grams over grams is typically, the common one that you would see. Any questions on that there? Other sort of concentration units that go with it is percent volume to volume, like in alcohol here. This is the volume of solute divided by the volume of solution times 100%. So this is typically, in most cases, milliliters over milliliters type of deal. There's also percent mass to volume, which is the mass of the solute over the volume of solution. And this is also times 100%. So much like before, if I had a 4.25% volume to volume sodium chloride solution, that would mean I have 4.25 milliliters of sodium chloride and 100 milliliters of solution, which again, you could use as a conversion factor, and you could flip it around if you needed to. If I had 4.25% mass to volume sodium chloride, that would mean I have 4.25 grams of sodium chloride over 100 milliliters of solution. It's kind of like density, grams per milliliter sort of deal. So again, that is how you could kind of turn the percentages into a conversion factor. You could also plug and chug into these equations as well. But if you want to take a more dimensional analysis approach, sometimes if you're given the percentage, either percent mass to mass, percent volume to volume, percent mass to volume, doing it more like a conversion factor is very helpful. These last two here, you probably don't have to be too careful about the bottom part. More so, it's really that first one, the percent mass to mass. I would say probably in a lot of cases, the volume of the solution would be given to you. They typically wouldn't, maybe in a lot of cases, separate the solute from the solvent in those type of problems with volume. But they could, but in a lot of cases they don't. But definitely in the mass sort of case, they very commonly like to kind of separate out the solute and the solvent from each other in the problem. Any question on those three types of percent concentration units there? All right, so let's try one here. A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams. So we're looking for the percent mass to mass, which again is the mass of the solute divided by the mass of the solution times 100%. So our calcium chloride here is going to be our solute, as it is the smaller thing, really. So our solute here will be 2.5 grams. The water here is going to be our solvent, as it is the larger part there. Going to be 50 grams. So remember that it is actually both of these things added together that will give us our mass of our solution. And we want to make sure we do not just go in with the solvent. So we would take 50 plus 2.5 grams, going to give us 52.5 grams. So that is, again, what we want to go in there on the bottom with, and obviously our 2.5 up on top. So our percent mass to mass will be 2.5 grams divided by 52.5 grams times 100%. So 2.5 divided by 52.5 times 100 going to give us 4.76%. And you can leave it percent mass to mass if you like, and you could add calcium chloride to it. Will look good. Any questions on that calculation there? So again, very common, this one, separate values given to you for both the solute and the solvent. Don't just take the solvent. Any questions? All right, so try another one here. Concentrated hydrochloric acid solution contains 37.2% HCl. What is the mass of HCl that's in 35.5 grams? Okay, so let's take a look. Once again, we're obviously dealing with percent mass to mass, which is our mass of solute, mass of solution, times 100%. So we are given, obviously, our 37.2% by mass of HCl. We also are given our mass of our solution, which is 35.5 grams, and we are looking for the mass of the solute, really. In this case, how do I know we're looking for the mass of the solute? Once again, we are looking for how much HCl there is, and remember that the solution's name is the solute. So if we're looking for the HCl, how much there is, that should be the mass of the solute. That's also why I know this guy is my solution. Otherwise, that would be really just the mass of the HCl by itself. So in this case, we could do a couple things. We could turn this into a conversion factor of 37.2 grams of HCl over 100 grams of solution, or again, 100 grams of solution is 37.2 grams of HCl. So if we want to take more of a dimensional analysis approach, we could take 35.5 grams of solution. We could use the proper conversion factor here, which is 37.2 grams of HCl and 100 grams of solution. Grams of solution will cancel, going to give us 35.5 times 37.2 divided by 100, about 13.2 grams of HCl in this case. That is pretty much the exact same thing you would get if you plugged and chugged into the equation. You would take 37.2% equals our mass of our solute divided by 35.5 grams times 100%. You basically would do that math right there is basically the same math, obviously. You would multiply to 35.5 to the other side and divide by 100, and you would get the same answer in that case. So, any questions on that one there? So percent concentrations are used occasionally, mass percent, volume to volume, and again, percent mass to volume is used. But we're going to then talk about really the most sort of common unit of concentration for solutions, and that really is molarity. So molarity is really the main sort of unit that we use most often with solutions. We do use some of these other ones along the way, but I would say out of them all, definitely molarity is the big one there. So molarity is basically moles per liter. Molarity is abbreviated with a big M, and it does stand for moles of solute per liter solution. And as we talked about in lab, you can really think of this as sort of a formula that you can use to solve for any of those things. And we do use it to solve for moles, liters, and molarity. If we wanted liters, it would be moles divided by molarity. If we wanted moles, it would be liters times molarity, which is a very common way that we use molarity, is this conversion. This is also really important to remind you that if you are using molarity and you're going to use volume to get to moles, which is a very common thing, you need it in liters, the volume, for it to properly cancel out and actually get you moles. A very common thing that sometimes people will do is they will multiply milliliters times molarity, and they think they get moles when they do that. And you actually do not get moles. You get what are known as millimoles, which are like moles, but 1,000 times not so much. Yeah, so these are actually millimoles in this case. So you probably are going to want moles when you do that calculation. So you need to make sure that if you are using molarity by itself, you should always convert it to liters. If you want to be safe in all situations, whenever you're using molarity, convert it to liters of volume, and you'll be safe in pretty much all your calculations, which might be the best way to go. The reason why these things sometimes work and why sometimes people will multiply milliliters by molarity is another version of molarity is actually millimoles divided by milliliter. And that's because if you take the milli on top and the milli on the bottom, they cancel and you're back to moles per liter, which is the same. So if you actually take milliliters and times it by the molarity and then divide by milliliters, it worked out okay. But I would highly recommend just going with liters and molarity always, and then you'll be sort of right. You won't be off by a factor of 1,000. So there is actually something you get when you do multiply by, like I said, they're milliliters, but probably not what you're looking for in your calculation. In most cases, you're looking for moles. So other things that we should be aware of when we use molarity is you should get rid of the big M when you do a calculation. And again, when you do a calculation, you should turn this into 4.2 moles of sodium chloride per liter. The number stays with the moles part, and it's always per 1 liter. That way you can kind of visually see both units. And when people leave it as big M, it is super common that they have no clue where the volume is or if there's even liters. And on their head, all they think is moles because I see M. So M is like moles. And that's all they think about and that type of thing. So highly recommend that when you do a calculation, you do not leave the big M in the calculation. You do more of a dimensional analysis approach where you see both of the units. That also means, by the way, if you needed to, you could flip this around and divide by it. And you could use this, as sort of another conversion factor where you kind of put the liters on top and the moles on the bottom. So I'd highly recommend not leaving the big M when you do calculations because you might get the wrong answer and not maybe remember where liters go. And it's also the very common thing people do when they do that. They multiply when they should divide when they should multiply because they really don't know where the liters part of it kind of plays into the units. So Any questions on that there? So a 1 molar solution of sodium chloride, and that's how you phrase it, 1M is 1 molar, would contain 1 mole of solute per liter solution. So how does the molarity work in terms of ions? So we know that when we do have a sodium chloride solution, really what we have are sodium ions and chloride ions in solution. That's really, what is floating around in that solution, as it is a strong electrolyte. So how does concentration sort of work from the whole thing to really what's happening in the solution? It works really like stoichiometry. And then what I mean by that is, if this was 1 molar, the whole thing, it is a 1-to-1 relationship between just the sodium ion. Its concentration would also be 1 molar, because you would take basically 1 times 1 gives you 1 molar. When we look at the chloride ion, it is a 1-to-1 relationship, which means you would take 1 times the concentration, and that would get you 1 molar as well. Now, let's say we had a 1 molar calcium chloride solution. When we take something like calcium chloride and it breaks apart into the solution, we get a calcium ion and 2, bless you, chloride ions. Now, when we take the concentration of the whole thing, which is 1 molar, if we were interested in just the calcium ions, and sometimes you're interested in just the one ion versus the other in a solution, we could see it is a 1-to-1 relationship between the two. And that means that we would take 1 times 1 molar, and we would have 1 molar calcium ions. But when we look at the chloride, it is a 1-to-2 relationship, which means we actually need to multiply the concentration by 2 in this case. And that will give us a 2 molar concentration for chloride. So what does that mean? It means pretty much what it sounds like. For every calcium ion that goes in, you get twice the amount of chloride ions floating around there. So there's twice as concentrated. So concentration is not additive. So clear, if you take 2 and 1, you don't get 1. Yeah. Or 1 and 1, you don't get 1 in the case up there. But it works like stoichiometry. So that's sort of the quick way that you could do that calculation if you're interested in just the ions. It's basically just like the mole-to-mole relationship. Let me just show you really the long version of that calculation so you can see how that comes. If we take our calcium chloride, for example, and we had our 1 molar calcium chloride per liter, we would do our mole-to-mole relationship, a 1-to-1 relationship here. So 1 mole of calcium chloride would give us 1 mole of calcium ions, and that would give us 1 mole per liter calcium ions. We do the same thing for our other ion, 1 mole of the whole thing per liter. It is a 1-to-2 relationship there. 1 mole of the whole thing gives us 2 moles of the chloride, and that gives us our 2 moles per liter of chloride ions. So that is where the multiply by 2 comes from. That is where the multiply by 1 comes from. It's really the stoichiometry of how it breaks apart in solution. So the quicker way is just multiply the concentration by how many ions you get of it. If this broke apart into a 1-to-3 relationship, you would take 3 times the concentration of the whole thing, and that would give you what the concentration of that ion would be. Any questions on molarity, how it relates to ions?